In this demo, we have just completed running the model inside the directory rom examples coriolis, and we're going to look at the tail of the log file to make sure the model is complete, and it's done, as you can see here. So now we're going to use MATLAB to plot the output of the model. So once again, remember the output is stored in directory out, and there's three files here. One is history, which contains the model output of the velocity fields and temperature and other state variables. Then there's also another file called floats.nc, which contains the trajectory of floats that I have released in the model to show, in fact, that the inertial oscillations make particles rotate in a clockwise direction, due to the inertial oscillation. The file rst.nc is a restart file, which is used if you wanted to restart the model. So let's go in the MATLAB trajectory, in the MATLAB shell here, and again, let's go into ROM's examples, coriolis, and here there's a directory called matlab, which contains some MATLAB scripts that will help you to visualize the results. Before plotting the model output, I'm going to execute this coriolis.m script, which contains a very simple solution of the inertial oscillations obtained by running different type of very simple numerical schemes like the Euler method, the explicit method of Euler, and then the implicit method, as well as the centered method. This is something that we also did in class. So I'm going to close here, run MATLAB, and ls, and I'm going to execute this script coriolis, okay, which is the solution obtained very simply in MATLAB of using simple numerical schemes. And if we plot it, here we have our plot. This axis is day, this is meters per second. So we see that there are all three different schemes, the explicit, the Euler implicit, and the centered, produce inertial oscillations. However, you can see that the blue one, which is the Euler explicit, is unstable in that the oscillation grows with time. Whether the red one, the implicit one, is overly stable in that if you see the red, the amplitude of the oscillation is decreasing in time. Whether the black one, which is the centered scheme, maintains and conserves the energy. So we're going to keep the centered scheme so that we can compare it actually to the ROM's output. So let's do that now. I'm going to close this, and I'm going to now plot the ROM's v-velocity using this script over here. I do that, and I get two lines. In blue, I have the ROM's simulated inertial oscillations, so I'm having the full three-dimensional complex model here, and you can see the blue line basically is just below the red line, which represents the solution of the centered scheme. So indeed, the ROM's model reproduces very simple dynamics such as the inertial oscillation correctly, and we could compare it to our centered scheme. The last MATLAB script is the one that plots the floats, and this one is just to show that if you put a particle if you track a particle in a domain that in a piece of ocean that it's undergoing inertial oscillation, they should move in terms of circles. And so here what you find is this is our computational domain in these white and black boxes, and these blue things, dots, are the trajectory of three floats as a function of time, and you can see that they've percursed a round circle, which is it's a perfect circle in fact, and this is the inertial oscillation, and now it's continuing to go around and around, and these dimensions here are in kilometers, so this is 120 kilometers in this direction, and this is the computational domain that we had for this model with periodic boundary in the north and the east-west. Okay, so given that we verified that indeed the floats are undergoing these circular orbits, which are rotating clockwise in the northern hemisphere, let's stop this and let's give a closer look at these scripts. Okay, so I'm just going to exit now MATLAB. Well, actually, I'm going to go to an editor window. I am currently in this directory here. So I'm going to go to an editor window here, and I'm going to go in this directory here, which is exactly where I am. Okay, and I'm going to start by looking at the first script, which is the one that plotted just the v velocity, and to show you how this looks like very quick. So the first thing I do in MATLAB is I clear the memory space, and then I have to open the netcdf file that contains the model output, and I do this by defining a new variable nc equals netcdf, and then in a string I put the name of the file, which is in the output directory. Now this nc is now an object that I can use to access the various fields. So here, for example, I say time equals nc ocean time, in graph the string here, the name of the variable ocean time, and then I put, open parentheses colon close parenthesis, and that what this does, it loads the value of the time array, this ocean time, into a local MATLAB variable called time. Okay. Now I want to since the model is in MKS units, this is seconds, I convert this into days by just doing this simple conversion. Then I select the I, J, K locations of my computational grid, meaning that that the grid, of course, has dimensions of kilometers, but in terms of the computational grid, I have nodes or grid points, and I want to select certain grid points where I want to extract the solution. In this case, I'm going to select grid point number 10 in the I, 10 in the J, and level 16 in the vertical. Now, of course, these inertial oscillation, by definition, the solution is the same everywhere in the domain because there's no space dependence in this particular example. So wherever I look in the computational domain, I should get the same solution, which if you verify it, you will find that it is the case. So now I can load the v velocity. I take the object nc, I put here now in between the graphs here, I put the name of the variable, and then I put the locations of where I want to extract the variable. So in this convention of the netcdf, the first index is time, so in this case I put a colon, which indicates that I'm loading all the time values, comma, k, which is the vertical dimension, and I want to load k, then j, which is the y dimension, and I, which is the x dimension. So in other words, instead of in the netcdf convention, the variables, are stored in reverse order. So they're not just x, y, z, and t, but they're actually t, z, y, and x. Okay, so then I use the command mfig to open a figure in MATLAB. I plot, this time array, which is the v velocity, and then here I compare with the output of the centered scheme, which I recompute using the centered scheme. So that's the first example, which was this plot v. Okay, so this will produce this result here. Okay, so let's go back to the editor window and let's look at the floats example. Floats. Okay, so in this case I have to load I have to open an netcdf file where the floats information are stored. Now the floats are not variables, state variables, but they're actually they're trajectories, and therefore they're stored in a different file, which is called floats.nc. So here what I do is I take the x locations and y locations, these are in physical space, so I extract these two variables. I start from time 2 to time end, and then the second array here is the number of floats, which in this case are 3, and I want to pick all the 3. Now I divide by 1000 because this domain is in the units are in meters, and since the domain is 120 kilometer by 120, I just want to have the dimensions in kilometers, so I divide by 1000 and get the kilometers. So this is the x and y trajectory. I close the netcdf file, then I open the history file of the model, and I open this because this file contains also information about the computational grid, the analytical one that we had set up. So I'm just going to load it, and these variables are stored in x_row and y_row. The reason why this has an underscore row, we'll talk about this later, but it has to do with the computational grid. It has to do with the fact that the model has several different computational grid at the same time. So, but this is something we'll look some other time. So again, I divide this by 1000. These arrays now are two-dimensional because it's a two-dimensional grid in the XY space. So now I do a figure. I plot, an empty grid. Those which is, if I show you here, if I plot this, so this would be the empty grid, would be these white boxes with black things, and then I tell MATLAB that the axes are equal, square, meaning that they're equally distant in the x and the y direction, so that the orbits that we're going to plot are going to exactly be circular. And now here I do a little loop for I that goes from 1 to the length of the array containing the trajectory. I plot as a blue dot the location of the drifter, and as I loop here I pause for 2 seconds so that this becomes a little movie, which is what you see here in this code here. Let me just rerun it real quick so you see that you have a little movie. So now you have these examples here contained in if you go in your where you ran the model, which is in this examples from Coriolis, you find these matlab examples inside the directory matlab, and so you can now play with this. So this is all for the plotting.